Yikers. Everyone's so cranky today.
One point.
What do you mean one point?
Only 1 point.
Well, they're not worth 1 point. You get like a 1 or a 0 in them. So if you look in your Canvas and you're confused about what your grade is, that's because Canvas sucks. So there's like each of the assignments is worth different amounts, right? It doesn't allow me to give individual weights. So for example, let's say we get to the end of the semester and I want to like remove one of the homeworks, or I want to change the value of one of the pieces because everyone did it or no one could complete such and such a thing. I can't just go in there and switch it. So I have a totally separate spreadsheet that I use that has a weighted average of your grades. Now, if you're doing really well in every component in the class, you're doing well in the class, right? So it's just sort of marking, did you do the lecture assignment? Make sense? Are you still upset? Okay. Other questions that are not about the midterm? It's great. Every time that we do a lecture, we start to see the stuff that's happening in the lecture. So like, we talked about atmospheres and how it's raining. So we really got to have a lecture on like winning the lottery. That would be really great. Okay. How many people finished that previous lecture tutorial? Okay, good. One? Okay. All right. Yeah. Oh, the last one? I have it in my office. We can get it to you afterwards. They're also posted. So if you go to Canvas and you can't see it there, let me know. Yeah. Yeah, what was the last one I gave out? Not the spectra, but greenhouse gases? Yeah. Yeah, if you have it, that's good. Should have waited. I mean, other than his baseball playoffs. Oh no. Yeah, lots of new TikToks, always. I want to have like, I should probably just have a second TikTok, which is just videos I like for my students, and I'll make all my likes visible. Yeah. What's that? Of course, yeah. Born and raised. Are you a Twins fan? No. What do you think? I'm not gonna say I don't let those two lives intersect. It's okay. That's not gonna say okay. Let me ask you a different question. Were you a fan of either of the results today? No. Are you watching it? Yeah, there you go. Okay. What? Yeah. Anything before we get started? Okay, I see most of you got my email about distributing it in midterm today, which is good. That won't happen towards the end, because otherwise you'll be sitting in there, you won't be able to hear anything that's happening. Okay. If there's questions on the midterm, I'm more than happy to talk to you about them, but probably not until the end of class, because we still have content to cover that will be on the exam. Okay. Okay. What's this? Atmosphere? Where? Here? And then more maybe on the right-hand side? So this is obviously not a real picture. No, like split screen that we took of Mars at different times. This is a visualization of what Mars's surface mostly looks like. It's got craters, it's got tectonic features. And yet when you see here, if you imagine a long time ago, there are places that look like there was probably standing bodies of water. So this is an artist's visualization of what those would look like if they were filled in. So if you look at something called Crater Lake, which is a misnomer, it's actually a volcano, but it looks like this here in Oregon, where there's a small peak in the middle, and then there's a lake all the way around. On the right-hand side, we have what we think Mars looked like many billions of years ago, and what it looks like today. One of the biggest questions we have is, how did it come to be that way? And we'll go into that today, okay? So we talked about these parts. We talked about weather as it comes from grabbing energy from the sun, why the structure of the atmosphere is entirely dependent on the types of light that are being received. Okay? And what we want to know is that question that I just asked. So how do you gain and lose atmospheric gases? And how can this explain our two nearest neighbors, which are Mars and Venus, right? Okay, so we're going to use all of these concepts together. We introduce something called greenhouse gases. We're going to use that on Mars. And we're going to talk about some stuff that we've never talked about. We're going to use that on, sorry, other way around. We're going to use that on Venus, greenhouse gas on Venus, and we're going to use some new processes on Mars. So what are the sources of atmosphere? Can anyone name a source of atmosphere? Yes, outgassing, right? Volcanic eruptions spew out gas that was underneath the crust. They put it outside of the crust. Anything else? Okay, here's some examples. So you had the one that we just mentioned, outgassing. It's also this one. It's called evaporation. So if you go to Santa Monica or to Long Beach and you see there's like a layer of fog, that's called the marine layer. What happens is that the ocean, the very surface of it, gets warm and it boils off. Just like when you left your top ramen on the stove for too long and then the water boils all the way down. Water goes from a liquid state to a gaseous state. And so then water goes from being in a liquid form to being in the atmosphere. Now, the same thing is true if you, for example, have ice. You can have ice on a surface, and rather than it going through the liquid form, it can sometimes just go directly to the vapor form. That's called sublimation. Okay? And then you have these weird ones over here. These are impacts of particles and photons. Photons are pieces of light smashing into the surface of something and releasing particles into the atmosphere. Okay? Now, they're ranked. So most of your atmosphere is coming from outgassing. Okay? Mostly what you're getting is water and CO2. And we're going to talk about these in more detail. There's some N2, there's some sulfur gases. This is what makes fart smell bad. Yeah. Yeah. So that's this process here too, evaporation. That's 100% that's me. So we have this large 70% ocean mass, right? When we look at the land area, we say that it's very small fraction of land, it's mostly ocean. And as that evaporates off, it becomes the water in the atmosphere. In fact, that's how we get drinking water. You evaporate it off the ocean, goes up into clouds, clouds go into land, it rains or it snows, and then that rain comes down in the form of fresh water Everyone familiar with that process? Or is that brand new information? Okay. All right. So why didn't Earth outgas as much CO2 as Venus? Is it because A, Earth didn't have as many volcanoes? B, volcanism was only active for a short period of time? C, Earth outgassed CO2 escaped the gravitational pull of the Earth? D, Earth's CO2 never made it out from the mantle? Or E, none of the above, it did outgas as much? So this when you're ready to vote. You're going to vote on 3, 2, 1. Okay, I see some different answers here. Anyone want to defend their answer? Yeah.
I was reading the book and I read that it was that the way outcast is much more emotional than CO2 is certainly what.
Yeah. Okay. So that helps if you actually know the answer. And in fact, it did outgas as much, but it's stored in rocks that we're quite familiar with. We just don't know that we're familiar with. They're called limestone and sandstone. We're going to talk about the CO2 sequestration cycle when we get to the latter half of this. But just because we have a different atmosphere than Venus doesn't mean that it didn't come originally from atmospheric outgassing. Okay? So there's more parts to the story. There's not just volcanism, but what happens to it afterwards. So this is an example here on Earth, obviously, of what is this called? A volcanic pit. And here you see direct outgassing into the atmosphere. Okay, so what are the ways we can lose atmosphere? So we have a source. The words we like to use when we get rid of something is called a sink. Think of it like you turn on the faucet of your sink. When the water comes out of the faucet and it goes down into the sink. So we have a couple different ways to lose it. One is to turn it back into what it was originally. So that can be condensation in the form of ice, or that can be condensation in the form of water. And evaporation, for example. If chemical reactions can bond with the rocks, change their material compounds. Up here, you can have thermal escape. Thermal escape is what happens when you have something evaporating, gets super hot, goes from being a liquid to being a gas, and that gas is very light, and then it runs away. And you can have this process that we're not going to go into in any detail called solar wind stripping. This is where energetic particles from the sun smash into the top of the atmosphere, give it a lot of energy, enough energy that it acts like an astronaut, says, I'm out of here, flies away forever. Okay. Questions about any of these processes? We're going to see them in practice in a few seconds. Okay. I'm going to skip this question. Let's talk about them as we think about Mars and Venus. Okay. We want to really answer this question. Why didn't Earth not end up like our nearest neighbors? I think that's a huge question. So first, let's look at Mars's atmosphere. We've talked about this briefly. It's primarily CO2. It's really cold, minus 20 to minus 50 degrees centigrade. I don't know what that is in Fahrenheit, but it's cold, below 0. And most of it is about 6/1000ths of our current pressure. So the way to think about this is that you're moving your hand through a fluid. You can kind of feel that when you do this. Just imagine that you were hitting about 1,000 less particles. So all of the forces that are being on your hand, the pressure that we feel, that's down by a factor of 1,000. Okay? So it's very thin, really thin atmosphere. And in fact, when we look at it, we see that there are polar caps the north and south, but it's mostly frozen CO2. So the CO2 in the Martian atmosphere freezes up directly and snows and makes the caps. And then in the summer, it evaporates, goes back into the atmosphere gets bigger. And then that CO2 and water heads back towards the other pole where it condenses and it snows out. Okay. And if you look here, this is part of the rover's tracks as it was driving. I forget which one this is. I assume it's Phoenix. What it does is it grabs with a little like cloth. And as it scrapes that top layer, you can see this white reflective material. What's that? Ice. In fact, that's water ice and CO2 ice just sitting right there under the surface. Why isn't it water, liquid water? It's too cold and really low pressures. Remember these pressures? They're about 1,000th the pressure at Earth. So on Earth, water needs to be both above freezing and at certain pressures in order to be liquid. So water cannot exist on Mars in sort of its normal state in a liquid form with these conditions. Does that make sense? Okay. And on the right-hand side, you see that there actually is some scattering. This is the sun, as seen from the surface of Mars. This is the color picture. It looks different because it's being scattered by something different from our atmosphere. It's being scattered by CO2. Okay. Let's talk about the history of Mars. The first 1 to 2 billion years of the interior of Mars, still warm inside. Right? So we're thinking about that analogy where we pull a potato and a pea out of the oven. Which one cools faster? The pea. The pea is the first one you can eat. You can't eat the potato yet until you smash it up and put the butter on, right? Okay. So at the beginning, this is still warm, even though it's small. If it's warm inside, what kind of processes do you get on the outside? Outgassing from volcanism. Okay, so we're tying these processes back to each other. So volcanoes are present when the interior is still warm. Okay. You also get tectonics. The thing is still moving around, still liquid inside. So you have motions. And this outgassing puts into the atmosphere greenhouse gases. We talked about greenhouse gases. We think that this was enough for liquid water. Now, why do we think there is liquid water? So we see evidence of liquid water. We saw that in the geology. We saw what looked like rivers. We saw what looked like when a stone falls in a river and all the edges get rounded. We found those stones. So we think there was probably weather of some form and erosion. We see canals, right, where a river would cut into the rock. Now that doesn't just happen really briefly, that has to happen with sustained water, okay? But clearly we just saw pictures of Mars. Every time we see it, there's no present water. So we want to understand how it may have disappeared. Another big question is whether or not it could have ever had the potential for life. When we talk about life towards the end of the semester, we'll talk about the history of life, which shows that on Earth, almost as soon as we had the conditions necessary for life, you had unicellular life, like that. Now, it would take multicellular life many billions of years to evolve, but almost right away, you had these weird little running around the place, okay? So then Mars cools down. Why does Mars cool down? Small. Okay, lots of these answers are straightforward. Small, cool down. Big, take a long time to cool down. And what happens? Volcanoes stop being volcanoes. They just become really large mountains. Okay? So let's look at what that looks like. Oops, this is too far. So you have this cold interior. you lose your magnetic field that's protecting the planet, and the solar wind stripping, which was a source of loss, starts to take effect. The cold interior means you don't have volcanism. You don't get any gas to replace any gas that's being lost. So typical evaporation happens right away. It's a cold atmosphere, so what happens is you start to condense it onto the surface. And I'm only mentioning loss process. I have no more sources, right? Because I don't have any more outgassing. Okay. And if you don't have a very thick atmosphere, this also means that those UV rays, which are normally absorbed at the top of the atmosphere, the X-rays that are absorbed at the top of the atmosphere, now they're making their way farther down. And they're doing chemistry deeper in. Okay. This breaks apart water. Hydrogen, is very light. In fact, it's the lightest element. So it makes its way to the top of the atmosphere because it diffuses. Oxygen sits below it. And when hydrogen sits at the very top, it's very easy for it to get enough energy to just say, bye, see you later. And then it leaves the atmosphere forever. Oxygen does this really fun thing. If you have a lot of oxygen in something, it likes to oxidize. So you'll see this when you drop a rock that's made of metal into the water and you wait. There's free oxygen inside of water just sitting there. That's what the fish breathe. And if you wait long enough, that piece of metal will get this weird orange. That's called oxidation, or the adding of oxygen. Okay. You have less atmosphere, it means you have less greenhouse gases. It means that you can keep the surface warm for less amount of time. So the gas freezes out. And we already talked about the fact that reflectivity was really important. So if you have a whole body that is entirely white, it's reflecting light. And so that doesn't help your problem either. You want to absorb more light from the sun, but now you're reflecting it. And you don't have an atmosphere to trap it in. Okay? This process makes sense? So you can no longer support liquid water on the surface. And the main reason for this was the main reason why all of this happens. Mars is small. Mars is small, so it cools fast. When it cools fast, the ability for it to have volcanoes is extinguished. There's no outgassing, there's no replacement of the atmosphere. So you have all these ways to lose it. And you just lose and lose and lose, and you don't replace any of the atmosphere, and it's a runaway process. Okay. So here's the example. Left-hand side, this is probably what early Mars looked like. Interior, magmatic, creating volcanoes. You see these little plumes there, putting atmosphere in. It's a big, thick atmosphere. Probably had something to shield the planet. And then as it cooled, volcanoes turn off, atmosphere gets torn away, and you don't have any replacement. This process makes sense? Okay, let's ask a question about it. What would happen to Mars today if it was moved to Earth's orbital distance? Would A, a greenhouse effect develop, leading to a pleasant Earth-like climate? B, runaway greenhouse would develop. Mars would be too hot to live on. C, polar caps would melt into the oceans, leading to a stable climate. D, some increase in its surface temperature, but still too cold for life. Or E, no change at all. You know you're ready to vote. Vote for this. Let's vote on 3, 2, 1. Okay, got a lot of non-voters here. Okay, let's turn to your nearest neighbor. Let's find out what they answered. If they didn't answer exactly what you answered, then ask them a question. If they did answer, find someone new. All right. Who walked it up? Yeah, no, but who do you know who on time? Of course. You can't let your dog, yeah. You can't give the stick. He's too good. He's too good. Okay, let's do a revote. Show me your fist. Everyone's ready to revote, right? No one's gonna not vote this time. I think I'm not looking at you. Okay, let's vote on 3, 2, 1. All right. That's good. A lot of people change their minds. I don't want to argue for one thing in particular. Yeah.
I choose
Okay.
because it exposes, I think that's going to have an impact on the surface temperature, but due to the fact that Mars is already almost there, then I don't think that life will happen because this
Okay. So you're saying there is a change in the surface temperature as we get closer. It's like when we get closer to a fire, it gets warmer. But your argument is that it's still too cold. Does anyone disagree? They want to make a point here? Go ahead.
And I'm thinking because closer to the sun, more global warming.
Okay, yeah, so that's maybe an open question here, right? Like, so how much greenhouse effect would develop, right? So this is a very acceptable answer because you don't know the temperatures that we would get until we move it closer, right? It is D, but if you thought A, I'm not saying that that's wrong, right? So this is the point of these questions that get you to think about the process as a whole. If you were to answer that and back it up in the exam, you said, I think it's A for this reason, and this reason, I would give you credit. Oh, interesting. Explaining your answers is why we do it in class, so you can succeed on the exam. Okay. Everyone's pissed about that, right? Okay. Let's talk about Venus. Venus is the example of everything that can go wrong will go wrong. So this is a real image. It's in black and white. But this is an image from the surface. So one thing that the beginning of the Cold War, we wanted to go to the moon. And then in order to go to the moon, the Russians were like, well, we're really good at shooting stuff off into space. So we're just going to shoot it in like every direction. And they kept landing on Venus. They were really good at it. We were not so good at landing on Venus. It's hard. You have to go through 90 times as much atmosphere. So you think about when we saw that meteor up at the observatory, this is something coming into the atmosphere at orbital speeds. You got to slow it down. So in general, that's pretty hard to do. It's not easy to do. We crash a lot of spacecraft. And so you want them to crash onto the surface and not up at the top of the atmosphere. The Russians were really good at landing. Problem is, you get down to the surface, you have about 30 minutes before the entire thing melts. So this thing here is 470 degrees Celsius. And let me tell you, circuits do not like to be at 470 degrees Celsius. Cameras do not like to exist at 470 degrees Celsius. If you were taking your phone, just left it in your car for like an hour, and then it's like complaining at you, it's like, warning battery too hot. That's like 120 degrees Fahrenheit. 212 degrees Fahrenheit is 100 degrees Celsius. So this is way, 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 way hot. okay? This is melting the actual metals. So we get these little pictures, they send them back, and nothing does. Okay, so how did this happen? How did it get to be this hellscape? You know, it takes this beautiful picture, and we can see some sort of features on here. I don't really see any like impact craters, but it's a very small image. I don't really see any lava flows. Again, small image. But it might look like it's a little weathered. Hard to say from these rocks. I clearly don't see any liquid water, right? Would you expect liquid water here? No. It all boil off, right? It's way too hot. So the question is, how did Venus come to be this hellscape? Okay. So feedback is something where I ask you for a question. You say the class is going really poorly. Right? I try to change the class so that it's better for you. Okay? Comes from this example of what happens when you make a change. So for example, I do this, grab this piece of chalk, and then push it. It rolls until it stops. Good, not a big deal. Unless push it that way and it falls off. So how does the change that I put into it, how does it end up either accelerating or decelerating the change? So if I rolled that chalk, friction slowed it down until it stopped moving again, that would be negative feedback. The change would be counteracted. If it fell off of the table, that would be positive feedback. The change is amplified. And we already saw an example of what happens to Mars's atmosphere as you stop putting out more atmosphere. So you have a couple problems. For example, one, ice starts to form. That makes it more reflective. Light doesn't make it down and be absorbed at the surface anymore. And because light is not being absorbed at the surface, it gets colder and more ice forms. So what of these two would that be an example of? I heard negative feedback, but it's actually positive feedback. The change is amplified. The production of ice creates more ice because the surface is more reflective and it's not able to accept as much light. Does that make sense? Okay. So we're going to talk about a positive feedback loop here that is called the runaway greenhouse effect. Here's another example, clouds. Let's say that the entire cloud cover of Earth increases. We talked about this a little briefly with nitrogen clouds. But here's the change, cloud cover increasing. There's two ways we can think about this. You can imagine that the new clouds, maybe they trap infrared radiation from the surface. And the troposphere warms. And that increases evaporation at the surface, say like at the oceans, puts more water vapor into the atmosphere. And then that creates more clouds. That makes sense? Or you could have them reflect more light that's coming in. And that would mean there's less energy at the surface. And that would mean evaporation cools down. And that would decrease cloud formation. If you're an Earth modeler, this is why you hate clouds. Because they do both of these things. It's very annoying to try and model. Okay? Clouds are very dependent on where they are, their exact composition, all of these things. So sometimes they increase cloud formation, and sometimes they decrease cloud formation. Okay? Here's another example. Which of these is the following of negative feedback? Is it A, a spooked cow causes a stampede? B, the hotter you get, the more you sweat? C, ice melts, making the surface darker and therefore warmer, causing more ice to melt? Or D, the rate at which the balance in an interest earnings savings account increases with time? I know these are all over the place, but I promise one of them is correct. Put up your fist if you're ready to vote. Vote on 3, 2, 1. Okay. Got pretty much an equal split between 3s and 2s. We didn't like this one? The picture of a cow? It's too obvious? Okay, we're gonna do that. All right. So what about this one? That one doesn't make any sense, right? Okay, so that is the rate at which the balance in an interest earning savings account increases at time. So that's like you put money into the savings account and it makes 6%. And then you get $106 the next month. And then that $106 makes 6%. Now that's more money. So this is an accelerated growth, not negative feedback. Let's cancel that one. Don't like that one. Cows make more cows scared. Okay, so which of these two do we think it might be? Yeah. Correct. So as you sweat, you actually get evaporation. This is what makes you cool. So you produce liquid on your surface. Your surface, I don't know, your skin, sorry. And that liquid then becomes vapor. And as it does that, it removes energy from your skin. Okay? And this one here, we can think through that. So this is sort of the opposite of that example I said earlier. Ice forms, and it creates colder conditions that causes more ice to form. Here's the opposite. Ice melts, making the surface darker, and therefore warmer, which causes more ice to melt. Okay, positive feedback. Now, this is a little annoying or confusing because the words positive usually mean good, and the words negative usually mean bad, but that is not what we're talking about here. So, for example, here you'd say, oh, that's a negative thing, so that's negative feedback. No, negative feedback is feedback which halts the original motion. So, for example, the more that you sweat, the cooler you get. Negative feedback. And you don't start sweating until you get too hot. Okay, let's look at Venus. Venus was as large as Earth, which means that it has volcanoes, yes or no? Yes. Lots of volcanoes. Still active volcanoes? Yes. Still active volcanoes. Still spewing out atmosphere. So it's the opposite problem that we had for Mars. Right? Mars cooled down, dead and boring. Okay? So there's ongoing volcanism and outgassing, and there's plenty of greenhouse gases. It's big. It holds on to that massive atmosphere. Okay? So what happens is you start adding those greenhouses, they start making the surface warm. This leads to high surface temperatures, also driven by closeness to the sun, and it's a runaway process. Let me show you. High temperatures take liquid water and turn it into steam. That sucks. Because when we talked about greenhouse gases, we said one of the most effective greenhouse gas is water. Water loves to absorb infrared radiation. That's how we make our microwaves work. Our burritos are warmed up by the water molecules inside the frozen burrito, right? You use microwaves, it heats it up, okay? So you turn the interior into steam. Now you're doing that to the atmosphere. It's really good at absorbing infrared. This creates a larger greenhouse effect, which leads to higher temperatures, which leads to more steam. Okay, a positive feedback. That make sense? Okay. So there's two versions of a positive feedback. They go in two different directions. So when we looked at Mars, it still was positive feedback. The ice on the surface made it colder, made it more reflective, made the atmosphere disappear. Here, it's the opposite. The addition of more atmosphere, making it warmer, turning any liquid water on the surface into steam, makes it warmer, which makes any liquid water that might form on the surface completely disappear. Okay? Let's look at a temperature profile. Here's Venus. You don't have to memorize this, I promise. Here you have your temperature way out at 700 degrees Kelvin. It's just a different form of temperature. And at the bottom, you have our troposphere, which we know and love. You have sulfuric acid haze. That's fun. So it has a different type of atmosphere than we do. And because there is constant outgassing, rather than having the nice rain that we have, it only has sulfuric acid, and it has sulfuric acid cloud tops. And its atmosphere is actually made of, what's the primary one? CO2. Okay, so let's have a look at that for a second. Where does an ocean's worth of steam go? Let's imagine, for the sake of argument, the Venus starts with exactly as much water as Earth. What are the options available to us? Okay, yeah, so imagine if we started with an ocean, and the evaporation would create the marine layer, and that would sort of recycle. Absolutely correct. What are the other ways that we could lose an ocean's worth of steam? Again? This one? Yeah. Okay, so that's a very good point. I usually like to say there's two options. It can go up or it can go down. Okay, so you could condense it onto the surface, but the surface is hot, remember? So it doesn't want to do that. It would rather stay in a vapor form. And in fact, the answer is that it went up. So it starts off in clouds, and ultraviolet light is making its way into the atmosphere, heating it up, dissociating it, breaking it apart, so that hydrogen, which is very light, escapes, and the oxygen hangs out with whoever's left. Whoever's left is CO2. Okay, with this process here on the right-hand side, you see oxidation at the surface. If you've ever seen pictures of what Venus looks like, they're in yellow. And then here, this is the removal of the atmosphere at the top. Okay, so solar UV breaks up water into H and O. H is lost by thermal escape, and O is lost by chemical reactions here, and also by being pulled off the top. Questions about this? So we're going to play the same game. We're going to move Venus. What happens to Venus if you move it to Earth's orbit today? Would A, runaway greenhouse reverse, leaving an Earth-like climate? B, some decrease in its temperature, but it's still too hot. CO2 in the atmosphere would condense, fall below freezing, no change at all. Or slight increase in its temperature, still way too hot. You ready to vote? It's your fifth. Vote on 3, 2, 1. I guess I don't know the trick name. Mostly twos. All right. Some decrease in its temperature, but it's still too hot. No one like that? We'd like to believe that. What's missing for A to be right? Yeah, so we're talking about 800 degrees, right? So 400 is still too hot for anything, right? Still burns everything to crisp. And in fact, what we're missing here is an ocean's worth of water, right? We really enjoy being in the ocean. You boil that all away, you have to give it back in order for us to have a good time, okay? So that's the big question, and the hint is already there, okay? So before I lose everyone, because they're like, wow, this is the worst class ever, we're gonna work on electric tutorial. So we're gonna perk our brains up a little bit more. So let's finish the one that we did last time. And then we also have another one. I think it's better to do this one on Thursday. Or would you rather work on the new one? Raise your hand if you'd rather work on the new one. Okay, so let's finish the one that we gave out last Thursday. Yeah. Yes, okay, that's a very good idea. If you weren't here last Thursday, let me give you the new one. Okay, smart. You guys want to work together? You can work on another one. Anyone else need one? Either. Yeah. So like is that? Oh, wait. I'm not very smart.
All of them. So let's say that you're in the community and figure out you have to consider that character is when you see the line that you have to walk that. Oh, I got it. We don't really have that meals in every stage is based on some people fall asleep and
Yeah, so you're going to then like so the reason that you put in charge of this very decision and you let them have You can also find them online too, if you want to like start looking at them. You don't have to right now, just saying. Okay, folks, if you're not quite done yet, that's okay. We're going to try and cram some more information into you, and then we'll stop about 5 minutes early to talk about the exam, unless people want to talk about the exam right now. Yeah. Raise your hand if you want to talk about the exam right now. Oh, no. Thankfully, it's only about a third, so majority rules. Okay, so we're going to skip over because we're going to quickly talk about climate stability. Okay, so climate stability requires something called the CO2 cycle. This is a picture that I kind of alluded to earlier, but it's called the hydrological cycle. Hydro being water, Logical, I don't know what that means, but hydrological cycle is the cycle having to do with water, okay? And it's pretty straightforward. You have water, it evaporates, becomes clouds, and then it gets cold and it rains. You know, that's unusual, but it happened today. So perfect timing for that. Sometimes it snows. You may or may not have seen that before. That'll happen at the top of mountains. And then that comes down, becomes a stuff called rivers and streams, and all of that heads back to the ocean. And the cycle starts again. So that one we might be familiar with, but there's also a CO2 cycle. And that one we're potentially not as familiar with. And it starts with CO2 being released from the interior of the planet, going into the atmosphere, and then being absorbed in the ocean. So the ocean is a liquid, and it's able to take in other gases. So we already said that there's oxygen inside of the water. That's how fish breathe. There's also CO2 inside of the water. It gets dissolved in there. And it turns out that that will be really important for climate stability on Earth. Okay? So we have just the right amount of greenhouse warming. Thankfully, we're all alive. Okay? Too much, be too hot, we'd all die. Too little, be too cold, we'd all die. So why do we say just the right amount? Because this has roughly stayed the right amount for about 4 billion years. At the very beginning, it was mostly magma. We don't really count that. But since there has been liquid oceans on the surface, there's been some climate fluctuations, but they haven't led to any of the two examples that we thought about earlier, whether that's Mars, fully iced over, or Venus, lost in oceans with the water. Okay? So that's going to be from this thing that we just talked about, the carbon cycle, and the idea of negative feedback. So here we like this idea, negative feedback. So the other ones were positive feedback. This one's negative, okay? Even though it's good. Okay. So CO2 is extremely soluble in liquid water. This is very convenient. What this means is that CO2 in a gaseous form interacting with water gets absorbed. What that means is that when ocean dissolve this gaseous CO2, you can trap it into carbonate rocks. And if we look back in this earlier picture, here, you can't exactly see it, it's not a great picture. If you have CO2 in here, making these rocks, and then rocks are heavy, so they sink, and sometimes they go under rocks. Sorry, they go under other rocks. And if they get far enough down, it gets hot and they melt. So CO2 that originally came out through outgassing into the atmosphere, dissolved into the ocean, turned into rocks, and then sunk back into the bed, starting the cycle all over. Okay? So that's the CO2 cycle in a 5 second.
Where do you go from the rocks? When it gets to the rock?
Yeah, so when it's a rock, it sometimes gets subducted, gets put underneath the crust into the magma again. So this is happening in places like the west coast of the Andes in South America. This is happening at any place that you have a major trench, like the Mariana Trench. You're recycling new crust. You're crushing it underneath the earth, not earth. Underneath the crust, I guess. Bad words. Okay. Here's Earth's built-in thermostat, and I'm going to show you how this works. Okay. We're going to follow just one side, and then we're going to follow just the other side. So let's start here on the left-hand side. When it's too cool, let's say the planet for some reason is too cold, then you have more clouds that are forming and less that are precipitating out. If you have less clouds that are precipitating out, then rainwater is going to dissolve less CO2. Less CO2 means more of it gets built up into the atmosphere, which is a very effective greenhouse gas, and it starts to warm up the Earth. Okay? So then you would have more precipitation and more dissolved or less dissolved CO2, and you would build up less CO2 in the atmosphere. You can see that on this side. Let's imagine that it's too warm. If it's too warm, you're going to have more precipitation. You're going to have a lot of evaporation, and that's going to rain out the CO2 from the atmosphere. It's going to dissolve it in the rainwater. The CO2 concentration decreasing means you have less greenhouse gas. That's going to cool the Earth down. Okay? So this one thing in our atmosphere plays both roles. But it plays both roles in the presence of water. And they work together to have this ocean to recycle CO2. If you don't have enough CO2 in the atmosphere, say on this side, if you're on this side, then it gets too cold, less precipitation, outgassing starts to build it back up again. Is this human timescales? Are we talking about like 10 years? No. This is tens of thousands of years. Okay. So these are like a blink in geologic times, but for us, this is far too long. And we'll talk about that in more detail. Suppose the Earth enters a major ice age. The oceans completely freeze over. How would Earth's atmospheric temperature change while the oceans are frozen, ignoring changes to albedo? Would it A, get warmer, B, get colder, C, stay about the same, or D, I can't tell? So we can just take that information, brand new information, use it right away. See your fist when you're ready to vote. This is actually related to the previous slide. Let's vote on 3, 2, 1. Okay, I got 1s and 2s. No one said it'd stay the same. No one said it was impossible. So I said that it was based on the previous one. Anyone want to argue for either of these? Let's go back to this picture. I freeze the oceans. What happens? Sorry, did you have your hand up? Okay. Uh-huh. Well, let's think about it in the context of this cycle. Okay. So if I freeze the oceans, what happens?
Because CO2 cycle.
Yeah, why is that?
And that's because according to the cycle, when it's really cold, then it's going to be it will reduce rain.
Right. So think about it this way. If you want to get rid of the amount of CO2, you have to dissolve it into the ocean. If the ocean's frozen, can it dissolve through the ice? No. So now CO2 starts to build up, starts to build up, starts to build up, starts to build up, and it gets hotter and hotter and hotter, and it melts the ice. Does that make sense? So if for some reason you got the whole world to freeze over, you're a Bond villain, and you get ice everywhere, magically, you just have to wait 10 or 12,000 years, and it'll all melt. No big deal, okay? Yeah, you killed everyone, but you didn't stop the Earth, okay? Okay. No, that's not too bad. Okay, so why did the Earth retain most of its water? Simple answer is almost always right. Just because it's big. Okay, so the 3 things that we want to look at is it's big, it holds on to its atmosphere, it has the right distance from the sun. That allows it for liquid water to exist on the surface, and it's rotating pretty good so that you can have like fun hurricanes and tornadoes and whatever weather effects that we know of. Okay. The most important part is that it's liquid on the surface, because if it wasn't liquid on the surface, we talked about briefly with the ice version, you build up CO2, it gets really hot, and then it melts again. So as long as you have water and CO2 interacting in this way, you have a climate stability. Does that make sense? Okay. Why does the Earth have so little carbon dioxide in the atmosphere? Rocks. Yes, that's the answer. Rocks. Okay. We already said this. Yeah, here's the answer. Limestone, carbonate rocks, you ever heard of the word carbonate rocks? It's like white, chalky rocks. It's literally rocky carbon. It's pretty cool. It collapses in your hand. It's not very strong, but it's pretty cool. Okay. I'm going to pause here because I think that's what people want, right? You want to keep talking about carbon, or do you want to talk about the exam? Okay, there we go. Oh, shit. Wait, hold on. Let's go back here. Yay, exam. Okay. Hey, your boo. Oh, my God. Okay, so let's talk about this. Any questions before we start talking about the exam? We'll talk about the questions on the exam now, but any questions about the last part before we talk about the exam? Okay, everyone understands the format? So the first thing that we're going to talk about is called metacognitive grading. Okay, you're like, what the fuck is it? So metacognition is just thinking about what you know. And I'm going to offer you the opportunity to have a metacognitive grading scheme. What does this mean? Let me explain. You'll like it, maybe. Here's the best case scenario. This is the one you want. For a single problem with 3 parts, you could get 100%. Great. In a traditional grading scheme, they would all be worth the same. So you get them all right, you get 100%. If you have them all the same, but it didn't matter what you know, you got one of them wrong, it's worth 66%. And if you get 2 of them wrong, worth 33%. And of course, if you get all of them wrong, it's worth 0, right? Okay, so this is the traditional grading scheme. I'm going to allow you to tell me which one you feel the most confident in. And that one will be worth more. And then the one that you feel least confident in will be worth less. So how does that work? Well, let's say you get one question wrong and you know what you know. Okay, you know that you just absolutely bombed the third part of that question. So you say, okay, you got the first 2 right. Now, instead of being worth 66, it's worth 85. Pretty good. Let's say you kind of know what you knew. So you got 2 of them wrong. Now, instead of being worth 66, it's worth 71. But if you bombed the part that you didn't understand, it's worth 42. That makes sense? You're saying, well, that doesn't really seem like a very good bargain yet. So look down here. Let's say you know what you know, and you bombed 2 of them. This is still worth 57%. Compared to 33%. Do you like this idea? Or is that too many numbers? But the exam wasn't until I got home. Why would you do this to me? Okay, so this is on the back of the schedule. If you go into the content schedule, you'll see this is the second one. If you have an issue with any of it, it's fairly straightforward, and I'm going to pass out the exams. You're going to see how it works. Everyone does this when they get the exam. You give the exam back and you put, least confident on every single one, and I'll just hand it right back to you and I'll have you erase it. Every part of the exam will have 3 parts. You have 1 question, 3 parts. 1 question, 3 parts. 1 question, 3 parts. And you're going to do this each individual section. Most, middle, least. That make sense? Okay. Yeah, so let's say question 1 has A, B, C. Okay. You can choose least, most, middle, whatever way you felt comfortable. But you can't do most, most, most. Okay. Everyone tries that at least once. Sure, one of you will try it. Okay, so that's this part here. Okay? We're all going to agree to that. We're going to agree that more words is better than less. So if it says, like, explain to me, and you write 1 word, that's not very good. Now, less words is better than none. So the easiest way to fail this exam is to write nothing. I encourage you not to write nothing. Okay? You also said that you wanted more questions. You said that. So I wrote more questions. You weren't here, you didn't get to vote. Okay? So each of the individual questions is worth less overall, which kind of makes sense. So now your whole exam is not based on 1 question, it's based on 7. There's been 8 weeks of classes. They're roughly commensurate with what we've gone over. Okay? So you all agreed to that too, right? Some of you more vigorously than others. Working together to answer a question is not permitted. I'm letting you take these home. You can look at your notes. You can look at your book. You can look at the slides. You can come to office hours. You can ask me questions on Slack or by email, but you cannot work together. And this is the only piece that I ask of you. Okay? If I catch you cheating, you get a 0. That's it. Okay? There's no reason. I don't like failing people. I don't want to fail you. If you don't have enough time, you want to talk to me, you want to clarify something, do that. Okay? Everyone in agreement?
Isn't Slack working together in a way?
No. You asking me questions.
Oh, okay.
Yeah. Good clarification. Good clarification. Let's not do that. Don't post like question 3. Hey, I got this. What did everyone else get? That's a no. Okay. Yeah. Keep in mind, you talk to your friend. You give them some advice on, section 2.3, and they just write down exactly what you said. What happens then? You both get 0, because I can't tell who asked who. So don't do that. Okay. Everyone happy?
So, if there's 7 questions, how do you pick both? We don't do.
You'll see. I'm going to pass these out.
The most.
Take one. Yeah. It's at the front with other people need them. I printed exactly 42. If I find it on everyone's favorite website, I'll be mad. You know what I'm talking about. Sorry. Thank you. Appreciate it. Yeah, that's okay. Awesome. Thank you. Wait, is your name on it? Yeah. Yes. Yeah. This one extra. And then like here are 2 electrical. Awesome. Thank you. Oh yeah. Thank you.